Japan now, though, their radiation levels in the seawater near the Fukushima plant continue to rise. They're now more than 3,500 times higher than normal. Radioactive materials also been detected in soil at the facility. Japan's government has described the situation as serious and unpredictable. Workers have been unsuccessfully trying to restore the plant's cooling system in what's now the worst atomic crisis since Chernobyl.
Iodine-131 was one of the contaminants released into the air and water. Clean drinking water was contaminated. Once absorbed into the body, radiation concentrates in the thyroid, causing damage and eventually cancer as it decays. Because of its adverse effects, we chose to focus on this contaminant and its removal from drinking water. This map shows the epicenter of the earthquake, which was 177 kilometers northeast of the Fukushima power plant.
The earthquake and resulting tsunami caused the power plant's cooling system to fail. This ultimately resulted in radioactive contamination being released. The fallout from the meltdown traveled out from the plant in a similar pattern to what's shown here. We designed a series of granulated activated carbon filters to treat the radiation. Granulated activated carbon, abbreviated GAC, is an effective and economical material for cleaning contaminants because of its physical properties. It has a series of macro, meso, and micropores that increase its surface area exponentially, allowing for high absorption rates. GAC is also relatively inexpensive compared to other methods of radioactivity removal.
To avoid clogging of the GAC filter, first the contaminated water must go through coagulation and flocculation processes. Next, the water would be filtered through a sand filter to remove the majority of the solids before water enters the GAC filters.
To have this happen in sequence, we would insert our unit operation after the filtration tank in an existing water treatment plant.
This is a schematic of our activated carbon contactor. You can see at the top there is piping for untreated wastewater influent and backwash effluent, and at the bottom there is piping for treated water effluent and backwash influent. The untreated water flows down through the top of the carbon bed and exits at the bottom, where it is then filtered through the second contactor. This is a schematic of our system with 3 parallel sets of 2 contactors in series, which is further explained here.
So here's a zoomed in version of our unit operation. It's made up of 2 filters in series, and then we have 3 sets of those. So the water comes from the filtration tank and then splits into 3 equal flows into each of the parallel filters. The first one has 50% removal, so it comes in with 210 becquerels per liter, and then it exits with 105 becquerels per liter, and then it goes through a 99% removal GAC filter, so it goes from 105 becquerels per liter to 0.1, which is the legal limit for drinking water.
And then that effluent is disinfected and then stored for drinking water.
To go ahead with our calculations, we made some assumptions about certain variables. First, we assumed the contamination level in untreated drinking water to be 210 becquerels per liter. We also assumed the acceptable level in the effluent water to be 0.1 becquerels per liter. Assuming the average person uses 374 liters of water per day, and we would have to treat for 400,000 people, we determined we would have to treat almost 150 million liters per day. Last, we assumed that iodine-131 could be treated like trichloroethylene because of the relative similarity in their molecular weights. We made this assumption so that we would be able to use the Freundlich adsorption isotherm constants for trichloroethylene, which were determined empirically and listed in the Wastewater Engineering Treatment and Reuse textbook. The following calculations were used to determine the bed life of our GAC filters based on our previously stated assumptions. Because we used 3 sets of 2 filters in the series, we split the flow of influent into thirds, which came out to be about 35,000 liters of water per minute. To determine the estimated bed contact time, we divided the 500 meters cubed bed volume by the flow and found our bed contact time to be about 14 minutes. Next, we had to determine the mass of GAC in the bed. By multiplying the bed contact time with the flow and the density of carbon,
we found that we would need about 225,000 kilograms of GAC. After calculating for the volume of GAC and then dividing that by the flow of water, we found our bed life for each GAC filter to be about 33 days, which would allow us to keep our filters in use for about a month before replacement.